Okay, so here we are treating limits and in their own right. Excuse me. So we can see from above that we can get an idea of the value of a function just by studying values near it. Remember when we went back to, we found the quote-unquote instantaneous speed here by using this method here with t equals 3 and t equals 3 plus h. We had substituted in for h 0.1. We knew that would give us a certain degree of accuracy. We knew that putting in 0.01 for the h would be to observe the motion at the 3rd second and the 3.01 second. And that is a pretty close comparison to just looking at the 3rd second. And then we knew that ultimately if we could use 0, then we could get the exact instant with no time delay. Okay, so basically a limit is what a function would turn out to equal, or what a function seems to be approaching as we get closer to a certain value for input. Okay, so process of finding elimination is called, or process of finding a value is called finding a limit. Okay. So anyway, there are many ways to do limits. You're supposed to do them by hand, really, but for the most part. But here's an example of a function where you're just going to use a table to kind of get the idea. So imagine f of x equals x cubed minus 8 over x minus 2. Okay, as tempting as it is to factor the difference of cubes, if you do know that factoring, let's not. Okay, what I want to do is I want to use my calculator and plug in 1.8. Okay, so I did that as 1.8 to the 3rd minus 8 all over 1.8 minus 2. Zoom in there. And this came out to be 10.84. And then plugging in 1.9 and doing the same thing, I got 11.41. Plugging in exactly 2 was a problem. I wasn't able to actually get a value there because on the bottom I was actually doing 2 minus 2, so that didn't work out. Now, a quick note on that. It is true that when I plugged in 2, that I got 2/3 minus 8 on the top, 2 to the 3rd minus 8 on the top, and 2 minus 2 on the bottom. So that would be 0 over 0. But that is not 1, that is not 0, that is just as undefined as anything else divided by 0. So please write undefined there. If you plug in 2.1, you get 12.61. If you plug in 2.2, it comes out to 13.24. I did all that ahead of time. But let's take a quick look at what this actually looks like. Okay, so you might remember your rational functions idea. It would seem that there's a vertical asymptote at x equals 2 here. Actually, that is not the case. What we have here is what we call a hole. If you were to graph this on your calculator as y1 and you did like a zoom standard, you would see that this graph does not have a vertical asymptote. The hole would not appear either. The calculator has difficulty displaying any sort of point discontinuity. Okay, but the table gives us an idea of what's going on. We can see here that, and we'll just focus in on the first quadrant. We're really only interested in going out to 2.2. So I'm going to make this 1 and 2. Okay, so that each space is 0.2. Alright, so let's take a quick look. 1.8 would be right in here. And it's up at 10.84. Okay, so I'm going to go ahead and make this go up to 15. So we'll do this as maybe, well, we'll just do this as 20. And then this will be 10. Okay. And actually, I think what I'll do is I'll treat this as, sorry for using pen, should be using pencil. Okay, so that'll make that 1.0, and that'll be 2.0. Okay, that gives me a little bit of margin. So each of these is 0.25, but that's close enough. Okay, so the idea is that at 1.8, the value came out to 10.84. So right about in here, we're talking about right about in here, somewhere. A little further over, 1.9, it goes up to 11.1, a little bit higher. At 2, it's undefined. So what does that mean? Well, it just means that there's no actual point there, so we can't plot. 2.1, just past 2, is at 12.61. So my drawing's not perfect. But you can see it's sort of a continuation. And we'll put in the hole in a minute here. Okay, and then at 2.2, somewhere right around 13 point something. Okay, so I don't know if that's very accurate, but the idea is at 2, we don't have a value. Not exactly at 2. Hold on, I'm calculating something here real quick. Okay, but it's close to about 12-ish. So right in here, there's like a hole in the graph, and the curve looks something like that. Now, f of 2 is not defined. We saw that a minute ago. But you could say that as you approach from the left or from the right, that we do seem to be in around the value y equals 12. Okay, so that is a pretty good guess as to what we think it is. And so I'm going to go ahead and write that the limit as x approaches 2 for this particular function, so you can write it like that, or you can put in the actual function itself. I'm going to go ahead and write 12 there. It's just a guess, but it seems to agree with my calculations. In other words, the value in the middle here, if I had to guess, I might go with the number 12. Let's take a look at this next one. Okay, for this one, here you have a function. Definitely going to need a calculator. Listen, radians mode. Okay? You don't want to be using degrees on this. You want to be using the radians mode. Okay, so you set your calculator y1 as sine x, and then divided by x. Make sure it's in the radian mode. Mine is. Alright, I use a TI-89, as some of you know. Okay, and we're interested this time in x equals 0, actually. I didn't state that. Oh yeah, I did, right here, as x approaches 0. And so you cannot plug in 0, but you can plug in these other values. So on the calculator, you could do this. Plug in negative 0.2. Alright, never mind the clicking. I'm just calculating that. Alright, it's 0.993347. This is approximately 0.994 or 993347. Okay, good enough. For the next value, I plugged it in, and it's 0.998334. I had trouble with this one. It's sine 0 over 0, both of which are 0, but again, we said that that's undefined. If you plug in 0.1, you get 0.998334. Notice the symmetry on that. The same thing we had for negative 0.1. It's interesting. And then we have 0.2. And for 0.2, I got 0.993347, as you might have guessed. First and last values in this table are equal. Okay, so everything is very, very close to 1. In fact, that's going to be my conclusion, that as you approach x equals 0, things seem to be getting towards 1. If you go ahead and mark this off and you plot it however carefully you wish, so if you make this like a 0.1, 0.2, and so on, we really only plotted a few points here, and they're all extremely close to 1, even closer than I'm showing here. And the actual graph here looks like comes down like that. You can look at it on your screen. I will show mine here. A little hard to see. Let me see if I can zoom in a bit. I'm going to turn on my light. Okay, so you can see the, if you zoom in further, that's actually the height of 1. But if you actually consult the table itself, you'll see that there is no actual point at 0. Rather, it's just near 0. So there's actually a hole there, and like I said before, the calculator doesn't know how to display that. You can zoom in as much as you want, but you will not find a hole there. It just fills it in as a pixel, I believe. Okay, so anyway, something like that. Alright, let's go on to the actual formal definition of a limit. And we'll begin this on our next video.